Question 1, A-Level Chemistry, Paper 2, 2022, June 2022. It says, an acidified solution of butanol reacts with iodine as shown. Draw the display formula for this. So for this, butanol, so this is what it's going to look like. C, 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 C. Now let's add the hydrogens. H, 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 H. Okay. Now we're going to have a double bond. O. We're going to have a CH2 and the iodine at the end. So CH3, CH2, CO, CH2I, the same form as this. Then it says give the name of this. Well, if we look at here, it's going to be 1-iodo, that's for sure. So 1-iodo, because iodine is on the first carbon. Butan, 4 carbons. And because the the 1O, the carbonyl group is on second carbon, butan 2O. So 1-iodo, butan 2O. You need to have dashes and all of that. And yeah, that's question 1.1. 1.2, calculate the value of the rate constant K for the reaction and give its units. So we know rate is equal to K, CH3, CH2, CO, CH3, and then times by H plus. So therefore rearrange it. K is equal to rate divided by CH3, CH2, CO, CH3, H plus. And we know that the initial rate of reaction is at 1.45 times by 10 to the power minus 4, and that the initial concentration of CH3, CH2, CO, CH3 is this 4.35 times by initial concentration of H plus 0.825 to 5. So K is equal to 1.45 times by 10 to the power minus 4 divided by 4.35 times by 0.825, and we get K is equal to 4.04 times by 10 to the power minus 5. Now the units, well, we know for the units, rates units is that mole per dm minus cube s to the power minus 1, so it's going to be mole per dm minus cube s to the power minus 1 over, well, we've got mole per dm minus cube for 1 and there's 2 of them, over mole per dm minus cubed squared. So we get s to the power minus 1 over mole per dm minus cubed, and therefore we get mole to the power minus 1 dm cubed s to the power minus 1. The reason it's mole to the power minus 1 and dm cubed because this is denominator, so you're going to do the opposite. So in this case, mole to the power of 1. So in this case, its final units could be mole to the power minus 1, mole to the power minus 1, dm cubed, and then s to the power minus 1. That remains the same because that is the numerator. Then it says calculate the initial rate of reaction when all of the initial concentrations are halved. Well, initial rate of reaction this, when the initial concentrations are halved, well, it's going to be a half times by a half, which will give me 1 over 4, right? So what does that tell me? Well, that tells me that the initial rate of reaction is going to decrease by a multiple of 4. Okay, we're going to times it by 1 over 4. So we're going to do 1.45 times by 10 to the power minus 4 times by 1 over 4. And then you get 3.6 25 times by 10 to the power minus 5, and the units 365 times by 10 to the power minus 5 units small p dm minus cube s to the power minus 1, given in the question already. 1.4. An experiment was done to measure the time taken for a solution of iodine to react completely when added to an excess of acidified solution of butanone. Suggest an observation used to judge when all the iodine had reacted. Well, remember iodine, so an observation to judge when all the iodine had reacted is that the idea that brown color is removed, hence goes colorless. So you could say brown color is removed, or you can just say colorless. Brown color is removed, hence goes colorless. 1.5. Describe and explain the shape of the graph in figure 1, 3 marks. Well, let's just have a look at it. We can tell that as temperature decreases, 1 over T increases, so that would be our first mark. Now to describe it, well, this is an exponential graph, so exponentially, and Y will the rate increase because more particles will have energy greater than or equal to activation energy, because more collisions, high number of frequency, more successful collisions, etc., etc. So as temperature increases, 1 over T increases. So that's the first mark. Just how does it increase? Exponentially. That's for your second mark. And then as many more particles have energy greater than or equal to EA, the activation energy. Now 1.6, reduce the time taken for the reaction at 35 degrees Celsius. So if we look here, 35 degrees Celsius, just draw a straight line up here. And what time will it give us? Will give us 0.03, 1 over T. So in order to find the time taken, all we're going to do is going to substitute this value into here. So it's going to be 0.03 is going to be 1 over 0.03, which will give me 33.3 recurring. Therefore we can say 33 seconds is the time taken for the reaction at 35 degrees Celsius. And then question 1.7, for different reaction, table 2 shows the value of the rate constant at different temperatures. This equation can be used to calculate activation energy EA. Calculate the value in kilojoules per mole to the power minus 1 of the activation energy EA. Gas constant R is 8.31 joules K to the power minus 1 mole to the power minus 1. So first things first, this does not look like a nice equation. I agree. I struggled with it the first time I attempted this question. Very hard. In fact, I didn't even attempt it. What we have to realize is we want to find activation energy. So first things first, let's just rearrange it. So what we can times by R, so we get ln R K1 divided by K2. Actually, if you times by R, it's going to be R ln. That's going to be a key difference. So times by R, so we're going to get R ln K1 divided by K2, and that is equal to EA 1 over T2 minus 1 over T1. And therefore to find EA activation energy is just going to be R ln K1 divided by K2, K1 divided by K2 divided by 1 over T2 minus 1 over T1. Now show the substitution of the values. So it's going to be R, which is 8.31, 8.31, ln K1, which is that, and K2, which is that. So 1.55, that's obviously going to be times 0.55 times by 10 to the power minus 5 divided by 1.70 times by 10 to the power minus 4 divided by 1 over T2, 1 over 333 in Kelvin, minus 1 over 303 in Kelvin. Now here's a quick trick. So we get EA is equal to, let's show the substitution, we get EA is equal to activation energy 66936 plus 7477. Now here's the trick. This is in joules. Remember, activation energy is going to be in joules. We want it in kilojoules mole to power minus 1. Remember, gas constant R is in joules, and activation energy is in joules, and we want in kilojoules per mole to power minus 1. So therefore, we have to divide it by 1000 to get into kilojoules per mole to power minus 1. So divided by 1000, 1, 2, 3, 66.9 kilojoules per mole to power minus 1 is your final answer for the activation energy. Question 1.8. Name and outline the mechanism for the reaction of butanone with KCN followed by dilute acid. Nucleophilic addition. Nucleophilic addition. What happens? Well, we've got butanone, straw that out, methane, ethane, propane, butane, CH3, CH2, and we've got the carbonyl group here. C double bond O, H, H, H. Now what's going to happen to KCN? So we're going to have a lone pair of electrons, Cn, that should be Cn with negative charge, and now this is partially positive, it's partially negative. Lone pair of electrons is going to attack partially positive carbon, transfer the electrons to the oxygen, and now what we're going to be left with CH H H C H H H C, oxygen with a lone pair of electrons and is negative, CH3 and a CN group. And now what's going to happen? Well, that's too easy. That's just nucleophilic substitution, right? Now what's going to happen is you've got a H plus, and this lone pair of electrons is going to bond from the oxygen, going to bond to the H plus, and now you're going to form C C C OH CN CH3 H H H H H. So now what is this called? Well, it's got an OH group and a CN group attached to it, so it's a hydroxynitrile. Hydroxynitriles are molecules with OH group and a CN group attached to it, but it doesn't ask us for that. It just wants to show the mechanism. So CN with a negative charge lone pair of electrons attack partially positive carbon, oxygen partially negative, C double bond O bond breaks, oxygen now has a lone pair of electrons and is negative and it bonds to a H plus, and then you form this, that is called a hydroxynitrile. And 21 marks for question 1. Yeah, it says it right here. Don't even need to count it. It says that 21 marks. And that is the end of question 1.